Yeah, so today we will discuss about the polar representation of bandpass signals. So, is it possible to say any one of you how do we represent? What is the standard form of representing signal or expressing the things in polar form? Like in Cartesian, I said na z is equal to x plus jy. We say right, and we will be able to say what is the magnitude and what is the phase. Similar to that in polar. Yes, in polar, how do we express polar form? You have not heard about this? Just say yes or no. If you don't know, I will continue. I will tell from my side.
Is it r and theta, sir?
Yeah. Yeah, r and theta, right? So r into e power j theta, something like that we write, right? So in the same way, so let me try to express the complex envelope of the bandpass signal in polar form. Okay. So let me write S tide of t. Okay. S tide of t is the what complex envelope of the bandpass signal. So I can express this in polar form as what in polar form is so okay. So as one of your friend rightly said, so I may be using the different variables. So I can say S tide of t is equal to, yeah, instead of r I am writing a of t into e power j phi of t. Okay. So r into e power j theta, right? So here I am writing a of t into e power j phi of t. So here a of t and phi of t are both real valued low pass functions. Okay. What I can say, a of t, okay, and phi of t are both real valued low pass functions. Okay. So now let me try to express the bandpass signal. Okay. So I know how do I write the bandpass signal. Any one of you can say, how can I write the bandpass signal? How do I define the bandpass signal? Yes. At least this you should be able to tell now the bandpass signal. Yes, how I can define the bandpass signal? Yes, you are not aware. How do I define the bandpass signal? And what we have learned so far? S of t. Yes, quickly I expect answer for this. How do I define the bandpass signal?
Si of t cos 2 pi of ct minus sq of t sin 2 pi of ct.
Yeah, of course, maybe many ways to say, right? I expect here to say in terms of usually we define, I think, shall I move up a little bit screen? More people have written. So today I'm discussing about the polar representation of the bandpass signals, right? I said the complex uh, envelope of the bandpass signal can be written in polar form as S tide of t is equal to A of t into e power j pi of t. Right? I said A of t and pi of t are both real valued low pass functions. So I can express the bandpass signal S of t as what? So yeah, of course it can be, there is the Cartesian form representation, what you said, Noreen. So the standard definition of bandpass signal S of t will be equal to what we say real part of, right, S tide of t, S tide of t into what? E power j 2 pi fct. Yes, is this fine? So S of t is equal to real part of S tide of t into e power j 2 pi fct. Now let me substitute the value of S tide of t here. So what I wrote earlier, na? I wrote S tide of t as what? In polar form. Just quickly, any one of you can say.
P of t into e power
Yes,
j5.
what did I wrote for S tide of t? Yeah, that is A of t into e power, right, j pi of t, right? Then this into e power j 2 pi fct. Okay, so let me further rewrite this as okay. Yes, what I can write? Real part of A of t into what? E power. If I take j outside, I can write 2 pi fct, right, plus pi of t. Is this fine? Yes, I'm asking, is this fine?
Yes, sir.
Yeah. So now let me create this as just theta. Okay. So I know how do I express e power j theta? E power j theta is equal to what? Any one of you can say?
Cos theta plus j sin theta.
Yeah. E power j theta will be equal to cos theta plus j sin theta, right? So what I said, theta is this, right? So if I substitute, means if I treat whatever is there in bracket as theta, right? Then a real part of that is what? Cos theta, right? So what I can write is, so I can write S of t, right? S of t will be equal to A of t, A of t, right? Into cosine of what? So theta is 2 pi fct plus pi of t. Okay. So this is the expression which what I can say is this is the polar representation of the bandpass signal. So I can express the bandpass signal in polar form as like this. S of t is equal to A of t cosine of 2 pi fct plus pi of t. Oh, sorry. Yeah. Okay. So here I can say A of t is the what? Envelope of the bandpass signal. So let me call, I think I have given the representation of bandpass signal in Cartesian form, right? In the canonical form. I think I have given equation number 3 now. Let me give this as equation number 4. If I am correct, you just, if I am not correct, just write the right equation number. Okay. So what I said here, A of t, right? A of t is what? It is the envelope of the bandpass signal. A of t is the envelope of A of t is the envelope of bandpass signal. And similarly, A of t is the envelope of the bandpass signal S of t. Okay. And similarly, Y of t is the what? Phase of the bandpass signal. Y of t is the phase of the bandpass signal. Just write in short, bandpass signal. Okay. So I can express the envelope, okay, A of t as what? And then A of t will be square root of S square of t, right? S square of t plus S square q of t. So this is my A of t, and the phase, right? Phi of t will be equal to what? Can write this as tan inverse of SQ of t by SI of t. By SI of t. Okay, hope this is clear. Yes, any doubt, any questions to ask in this? Hope everybody will be able to understand what I said. How do I represent the bandpass signal in terms of polar form? Yes, do you have any questions or shall I go ahead?
So can you scroll up, sir?
Scroll up. Okay. From where?
Sir, where did you mark equation 3, sir?
Equation 3 is what I wrote. No, that is in Cartesian form, man. Cartesian form is what? S of t is equal to Si of t into cosine of 2 pi fct, right? Minus Sq of t into sine of 2 pi fct. I gave number for that as equation 3. While discussing Cartesian form, right? That is
Okay.
S tide of t is equal to, huh?
S of t is equal to Si of t cos 2 pi fct minus Sq of t sin 2 pi fct. That's one, sir.
Yeah. That is, I think I numbered equation as 3.
Yes, sir.
Okay. Yeah. So these are the two ways to represent the bandpass signal. One in Cartesian form, another one is in polar form. Okay. Is this fine?
Yes, sir.
Yeah. Okay. Now, okay. Yeah, I can find out what is SI of t and SQ of t from the equation 4 also. So let me just say, how do I find SI of t and SQ of t? Okay. So let me write what I said, the S of t, right? S of t will be equal to A of t into cosine of 2 pi fct plus pi of t. So I can treat uh, this as A, okay, this as A and this one as B. And you all know what is cos of A plus B. Any one of you can say what is cos of A plus B? Just quickly expect answer for this because they're all basic things now. Many times we might have repeated. Yeah, cos of A plus B.
Cos A cos B minus sin A sin B.
Yeah, so cos of A plus B will be what? Cos A cos B minus sin A sin B. Just I said what is A and what is B now. So let us express S of t in this. So just let me write S of t is equal to A of t. Okay. And therefore S of t is equal to A of t into cos 2 pi fct, right, into cos pi of t, okay, then minus A of t into sine of 2 pi fct into sine pi t, right? Just let me go that side. Okay. So I can write sine into pi of t. Okay. So I can rewrite the above expression as what A of t cos pi of t, okay, into I will write cos of 2 pi fct, okay, then minus A of t to sine pi of t into sine of 2 pi fct. So any one of you can guess what will be Si of t and what is Sq of t? Hope you're understanding what I'm asking. Can I say this as something into cos is what Si of t, right? And then something into sine is the Sq of t. So to say in Cartesian form, right? We have wrote Si of t as that is S of t as what? Si of t into cos 2 pi fct, right? Minus Sq of t into sin 2 pi fct. Therefore, I can say Si of t will be equal to what? A of t into cos pi of t. Okay. And Sq of t and Sq of t will be equal to A of t into sine of phi of t into sine phi of t. Okay. Yes, is this fine? So just I am playing with this basic mathematical relations. Okay. Just I took cos of 2 pi f c t plus phi of t as what? The two terms. First term as a and second term as b. Then I expanded by using cos of a plus b as cos a cos b minus sin a sin b. So I could bring it to this form. Then I am saying what is the in phase component and what is potential phase component. Okay. So to conclude, what I can say is with respect to the signal representation, bandpass signal representation, okay, there are two ways to represent this bandpass signal. One is in Cartesian form, another one is in polar form. Okay, so hope you have understood the difference and as well as how I wrote the representation of this bandpass signal in Cartesian and polar form. So to summarize, what I can say is in Cartesian form, just I will read bandpass signal. Okay, bandpass signal in canonical form or what we can say Cartesian form. In Cartesian form will be what? It will be S of t is equal to Si of t cosine of 2 pi f c t minus sq of t sine of 2 pi f c t. Okay, so in the same way, the bandpass signal, BP signal, so this is first one and this one is the second one. BP signal, that is bandpass signal in polar form. Okay, in polar form, it can be written as what? S of t will be equal to A of t, the cosine of 2 pi f c t plus phi of t. Okay, what I said, A of t is the envelope and phi of t is the phase of the signal. Okay, so this is all about the representation of bandpass signal in Cartesian and as well as polar form. Yes, any questions to ask? If you have any doubts, any questions to ask, you can ask. Yes, do you have any questions I'm asking?
No, sir.
So shall I proceed then? Okay. Okay. So now we'll discuss how to represent the bandpass system, okay, in terms of its complex low pass. So far we were discussing about the representation of bandpass signal in terms of its complex low pass, right? In the same way, so now let us try to discuss how we can represent the bandpass system in terms of its complex low pass. Okay. So next topic is what? Complex low pass representations. Complex low pass complex low-pass representations of bandpass systems. So now we are discussing about system, not the signal. Okay. Bandpass systems. Yeah. Complex low-pass representation of bandpass system. So let us again begin with our understanding about the representation of bandpass system as a equivalent complex low-pass system. Let us start with signal. So let me consider a narrowband signal. So it is basically what a bandpass signal, right? Let's consider. So I hope I'm using different terms. So far I used to say bandpass signal. Now I am calling it as narrowband signal. So this narrowband and bandpass are interchangeable. Okay. So let us consider a narrowband signal. Narrowband signal, so which is denoted as S of t. So narrowband signal or bandpass signal, both are same. Okay, so and I can say S of t, its Fourier transform will be what? S of f I can write, right? Sorry. So its Fourier transform will be S of t. So already I told what is bandpass signal, how do we represent and all. I expect you people to quickly say what it is. How can I express or how can I represent graphically the bandpass signal? Yes, quickly. I don't want to waste much time on this because I thought that just in the last two classes. Yes, come on. I expect answer from you people. Bandpass signal. How do I represent the bandpass signal?
Triangular wave, sir.
Triangular wave which appears at plus or minus fc, right? Having a bandwidth of 2w. Only Skanda is talking. What about others? So very few people are interactive. So other people are sleeping or what? So now I'm finding it around 48 students, right? Out of 48, only Skanda only says always about any basic questions like cos of a plus b, whatever. He responds. What others? And Anand, Prajwal, Naurin, very few. Others also should open up their mouth. Na? They should be interactive. I need not again call every day. Yes, we have to be interactive and all. These basic questions you should be able to share. It is not that just one way. So I already I said how do I represent that. So I can just recap that, right? So this is my frequency. I can say at plus or minus fc will be my signal will be around plus or minus fc. Okay. So this is how I represent the bandpass signal in frequency domain. Okay, and it's a magnitude of 1. And what I can say, this value is fc plus w, right? And this value is fc plus w, and this value is fc minus w. With that, I can say the bandwidth of the signal will be how much? Any one of you? other than Skanda and whoever is interacting, other people should tell what is the bandwidth of this signal. I can say
2 FC, sir.
yeah, it is. Yes, someone has said some value.
2 FC, sir.
How much?
Sorry, sir. 2 omega.
How it is? 2 omega or 2W, right? Because see, bandwidth means upper frequency minus the lower frequency. I need not write every time. Upper frequency is Fc plus W and lower frequency is Fc minus W, right? So it will be 2W. I can say the bandwidth will be 2W. And the carrier frequency, usually for bandpass signal, we say the carrier frequency will be much higher than the the signal frequency. Okay, so Fc will be greater than W. Okay, so this is how I represent graphically. So just why I'm telling is I need to relate this bandpass signal with respect to the bandpass system. That is how I took up this bandpass signal or a narrowband signal. Okay. So I am assuming that the spectrum of the signal is limited to frequencies within plus or minus W hertz of the carrier frequency Fc, right? And also I said Fc will be much greater than W. And now let me apply this bandpass signal or narrowband signal to a bandpass system. Okay. Let me apply this bandpass signal to a bandpass system. I am considering that bandpass system as an LTI system. Okay. Then what I can write is, so this is my bandpass signal, a narrowband signal. I am applying this narrowband signal to what? This is my bandpass system. Okay. And it is basically an LTI system. This is a bandpass system. Okay, and as I said, it is basically an LTI system. I hope you all know what is LTI system, right? A linear time invariant system having an impulse response. Having an impulse response, I can represent the impulse response of this bandpass system by h of t. Okay, and its frequency response will be h of f. All know these conventions. So this is what? This is the impulse response. This is the impulse response of the bandpass system. And h of f is the frequency response. This one is the frequency response. Okay, so why I'm considering means I need to represent this bandpass system as its equivalent complex low pass representation. To understand that, so I am applying this bandpass signal to the LTI system, which is basically a bandpass system having impulse response h of t and frequency response h of f. And I also assume that the frequency response of this bandpass system, okay, the frequency response of this bandpass system is also limited to the frequencies within plus or minus b hertz of the carrier frequency. Okay, so this is another assumption what I'm making. I'm also making an assumption that assume that the frequency response, okay, the frequency response of the system, that is bandpass system, okay, is limited. Frequency response of the bandpass system is limited to frequencies, within plus or minus b hertz of the carrier frequency, plus or minus b hertz of carrier frequency. Means I am restricting the bandwidth of the system also. Okay. So what I wanted to say is the bandwidth of the system is also less than or equal to the signal bandwidth. I said what is the signal bandwidth? The signal bandwidth is 2W, right? And system bandwidth is plus or minus b hertz. So what I can say is the system bandwidth will be
Sir?
less than or equal to the signal bandwidth. Yes, any questions?
Sir, what is the word after frequency, sir?
After frequency, where?
Second line.
Yeah, this one, huh?
Below that.
This
Below
one, huh?
that. Below that, sir.
Here, huh? This one, within plus or minus b hertz. This word is within. I am saying the frequency response of the system is limited to frequencies within plus or minus b hertz. So that within is not clear. Let me rewrite. Okay. Within. Okay, within plus or minus b hertz. Okay. I said now this is what 2b is the system bandwidth. That is bandpass system bandwidth. Okay. This one is system bandwidth. And this is what? This is the input signal bandwidth. Okay. So my input signal is also bandpass signal, and my system is also bandpass system. So input signal bandwidth it is. So this is the assumption what I am making. Okay. The system bandwidth will be less than or equal to the input signal bandwidth. Okay. So now let me represent the impulse response of this bandpass system, h of t. Okay, h of t means how I used to represent the bandpass signal in terms of in phase and quadrature phase component. So similar to that, I can express the impulse response of the bandpass system in terms of in phase and quadrature phase components. Yeah. So the bandpass system with impulse response the bandpass system with impulse response. Impulse response I denote by h of t. Okay, is given by I said now how do I represent the impulse response of the bandpass system? So h of t will be equal to hi of t into cosine of 2 pi fct minus hq of t into sine of 2 pi fct. Okay. So I can express the impulse response of the bandpass system like this. The h of t is equal to hi of t cos of 2 pi fct minus hq of t sine of 2 pi fct. Okay. So the complex impulse response of this bandpass system, how do I write in terms of Cartesian form? This is in a canonical form, what I can say, right? So I know the just if you understand signal, then it becomes easy for writing the impulse response in the same way. Okay? The complex impulse response. The complex impulse response of the bandpass system. Of the bandpass system is, yes, how do I express the complex impulse response in Cartesian form? Yes, complex impulse response, that is h tide of t. Okay, h tide of t will be equal to, I can write what, hi of t, okay, plus j into hq of t. See, whatever I used to write for signal, I am writing here for system. So here I expressed the impulse response of the system, the bandpass system, as what? Hi of t cos of 2 pi of ct minus hq of t sin of 2 pi of ct. I am writing the complex impulse response of the bandpass system as what, hi of t plus j into hq of t. Right? So I can express this h of t similar to the bandpass signal. So I think I expressed the bandpass signal as what? S of t is equal to real part of s tide of t into e power j 2 pi of ct. Na? In the same way, I can express the impulse response of the signal in terms of the complex impulse response. Okay, so let me write. Okay. We may express we may express the impulse response, h of t, right, in terms of h tide of t, in terms of h tide of t. So how can I write in h of t in terms of h tide of t? So h of t is equal to I can write h of t, right, will be equal to real part of h tide of t into e power j 2 pi fct. Okay, so this is how we express the impulse response of the bandpass system. Okay, in terms of complex envelope of the impulse response of the bandpass system, right? So here this is hi of t and this hq of t, and as well as this h tide of t. Okay, so these are all what is what I can say. Hi of t, hq of t, and h tide of t are all, they are low pass functions or high pass functions.
Low pass.
Yes, no idea. Yeah, they are all low pass functions, right? So I can say where hi of t, hq of t, and h tide of t are all are all low pass functions. Are all low pass functions, and their frequency band is limited to less than or equal to the system bandwidth. Okay. So limited to the frequency band, limited to the frequency band limited to the frequency band of what? So this will be less than B and greater than or equal to minus B. Okay. Is this fine? So this is all in time domain. In the same way we can do it in the frequency domain also. I think I will leave it to that. Can I leave it to you people only? In the same way it can be done in frequency domain also. Okay. Hope you understood how do we find the impulse response of a bandpass system. That is, it's a complex low pass representation. That is a complex low pass representation is what? H tilde of t, right? So which is equal to hi of t plus j hq of t. So I will be able to determine this h tilde of t, right, by using this. Yes, if you have any questions, you can ask. So far, I discussed about how I can represent the bandpass system in terms of its complex low-pass representation. And I'm leaving the frequency domain representation to you people only. You should only find out how it can be done. If you're not getting, then I can help. So with this, then the next topic will be, let us consider, now we have discussed separately, right? How do we represent the bandpass signal in terms of its complex low pass signal, and as well as how do we represent the bandpass system in terms of its equivalent complex low pass system, right? So now together we need to represent both signal and system. Okay, so that will be the next topic, that is complex representations of bandpass signals and systems. Yes, I'm asking any questions you have. Who has joined now? A few people have joined now. What, Gayatri, you raised your hand, why?
Sir, by mistake, sir.
By mistake, okay. Yes, just now some people have joined. Who has joined? Just let me pull out. All these people were there in the earlier. Yes, Siddharth. Siddharth Atre. Siddharth. That fellow has left the. So, yes, Tipana.
Yes, sir.
Are you understanding, man, what I'm saying?
Yes, sir.
Okay. Okay, fine. Just let me take up the next topic, that is the complex representation of bandpass signals and systems. So as I said, how I represented in time domain, in the same way it can be represented in frequency domain also. Just I'm leaving it that part to you people. Okay. Okay. So next one is the complex representations of complex representations of bandpass signals and systems. Yeah, I think two things we have discussed. At least I expect you people to say just how do I represent the bandpass signal, okay, in terms of its complex low pass and as well as the bandpass system. I expect you people to tell the equation. Yeah, quickly, anyone of you can say how can I represent the bandpass signal? Bandpass signal. So many times I'm repeating bandpass signal. The definition of bandpass signal, that is, see, how can I express the bandpass signal in terms of the complex envelope? Bandpass signal in terms of the complex envelope. So S of t is equal to what I said, real part of S tide of t, right, into e power j2 pi fct. Why you people don't understand the question? So this is the representation of bandpass signal, okay, in terms of the complex envelope. What is complex envelope here? S tide of t is the complex envelope, right? So this is how I represent the bandpass signal in terms of the complex envelope S tide of t. Okay. So bandpass signal I need not write. So this is, you should be able to understand this is a bandpass signal. In the same way, how can I express the bandpass system in terms of there is bandpass system with impulse response S of t in terms of the complex impulse response S tide of t of the system? See, h of t is equal to, right, real part of h tide of t into e power j2 pi ct. Just now I discussed this, right? So first one is for signal, second one is for system. Okay. So this is for what? This is for bandpass signal, right? How do I express the bandpass signal in terms of the complex envelope? And this is for what I said, this is for bandpass system. So how do I express the impulse response of the bandpass system in terms of its complex impulse response, the state of t of the bandpass system? So in both the equations, what we are finding is it possible to say what we are finding in both the expressions, S of t and as well as h of t, right? We are saying real part of S tide of t into e power j2 pi ct, and here h of t is equal to S tide of t into e power j2 pi ct. See what you are observing in both the equations? You are not observing anything.
We are considering only the real parts.
See, there is an exponential factor, right? Hope you could observe the exponential factor in both equation 1 and equation 2. So the presence of this exponential factor complicates the analysis of the bandpass system driven by the bandpass signal. Okay, so second equation is about system, right? The first equation is about the signal. So the presence of this exponential factor, okay, in both the equations, what I said, it will complicate the analysis of the bandpass system driven by the bandpass signal, that is S of t, right? So this analysis will be able to simplify through the combined use of this complex low-pass equivalent representation of both the signal and as well as the system. Okay, so we characterize the bandpass system with the impulse response h of t and the bandpass signal by the s side of t. So let us see how it is going to simplify the analysis of the bandpass system driven by a bandpass signal without the use of this exponential factor by representing both this bandpass signal and as well as system by its complex low-pass representations. Okay, so I think let me stop with this. Let me continue the next class about that.